Hello and welcome back, everybody. My name is Yannick Krivka. I'm a PhD student at ETH Zurich, and this is my second talk as part of the NCNGT 2021 conference. And I will talk about the IRS compactification of moduli space. So as I said, this is the second of two videos. In the first part, I introduced invariant random subgroups, or IRSs for short, and I constructed the IRS compactification of moduli space. And today, I want to talk a little about the description of the IRS compactification of moduli space. So before I start straight away with that, I would like to do a short recap from part one. So first of all, I would like to reintroduce some notation that I set in the first video. So in particular, in the following, I will use the letter G to denote the group of orientation preserving isometries of the hyperbolic plane, which is isomorphic to PSL2R, and in fact, PSL2R acts via Möbius transformation on the hyperbolic plane. Second of all, one of the central objects here, the space of invariant random subgroups, I denote by IRS of G, and it's naturally equipped with its weak star topology, which turns it into a compact space, as we saw in the first video. Moreover, I picked a topological surface, an oriented topological surface with possibly punctures, but no boundary and negative Euler characteristic. I denote it by sigma, and this is the surface that we will equip with finite area hyperbolic structures. And that's exactly what brings us to the moduli space of finite area hyperbolic structures on sigma, which I denoted by M sigma here. Okay, so much for the standing notation from part one. Now in part one, as I said, we constructed the IRS compactification. Let me tell you again how that worked very briefly. So recall that for any lattice in G, we constructed an IRS mu gamma, and this mu gamma was constructed as follows. So because the lattice gamma, because the lattice is a lattice, there is a unique invariant probability measure on the quotient G mod gamma. And in fact, we obtain a probability measure preserving action of G on this quotient here. And via its stabilizer map, we could push the invariant probability measure nu gamma to an IRS mu gamma of G, and this stabilizer map is just given by this phi gamma, which associates to every coset. Here, it's associated conjugate. So that's how we got from a lattice here to an IRS. And we use this construction to put the moduli space inside the space of invariant random subgroups, and that worked precisely as follows. So we constructed this map iota from the moduli space to the space of invariant random subgroups by associating to each hyperbolic surface X, which we may always write as the quotient of the hyperbolic plane by some lattice gamma here, by sending this quotient here, this hyperbolic surface, to the constructed mu gamma. And not only is this map well defined, but it's in fact a topological embedding. And as I just said, IRS of G, the space of invariant random subgroups here, is compact. So when we take the closure of its image, in here we obtain a compact set, and that is precisely how we define the IRS compactification of the moduli space. So we put the moduli space in IRS of G and we take the closure. Okay, and at the end of the first talk, I closed with the question, what is the IRS compactification? And this is in fact what we want to answer in this talk. And we will answer this question by relating the IRS compactification to another compactification of the moduli space, which is maybe more known. To me, it's the augmented moduli space, but if you like to talk about smooth algebraic curves, you might instead prefer to talk about the Deligne Mumford compactification, which I will denote in the following by M hat here. So before I can use the augmented moduli space to describe the IRS compactification, I should use a couple of words about the augmented moduli space. So what is the augmented moduli space? It's another kind of compactification of the moduli space, and the basic idea is to allow for curves in your surface to collapse to nodes as you move your hyperbolic surface to infinity in the moduli space. So let me give you a picture. So here we have our hyperbolic surface. Actually, we have a sequence of hyperbolic surfaces in this moduli space, and we look at this closed curve here, and we assume that this sequence is such the lengths of the curve Cn here tend to 0 as n tends to infinity. And the idea of the augmented moduli space is to put a limiting object at the end of such a sequence, which looks like a nodal surface here. I will denote this by this decorated X here, where the curve here just collapsed to a single point in here, and we have finite area hyperbolic structures on the remaining two parts. Okay, and that's the idea. Let me give you a mock definition of the augmented moduli space. So of course, there is more to say about this, but in favor of a brief exposition, I would just mention the parts that we need to know about. So the definition of the augmented moduli space for me is it's just the space of nodal surfaces. And now, as I tried to explain before in the picture, a nodal surface comes with a bunch of data. One, it comes with a possible empty family of disjoint essential simple closed curves in our surface. These are those that you can think of as collapsed down to nodes. And on the complementary parts, on the connected components in the complement, we have a finite area hyperbolic structure, which means that we can associate points in the moduli space of its parts. And in fact, we will call these xi then also the parts of this nodal surface. And let me stress, this collection of curves is in fact important, and it encodes to us how these xi's fit together at their cusps in a way. So a different sigma gives us also a different kind of nodal surface generically. Of course, there are exceptions to this, but in general, picking a different sigma gives us a different nodal surface. And as I mentioned here, possibly empty. So that's in fact important, because in this way, our moduli space sits in the augmented moduli space as these nodal surfaces, which have actually no nodes at all, meaning that there's no family of simple closed curves that got collapsed to a point. So let me give you another example of this data of such a nodal surface. So here we are in the topological setting. This is our topological surface sigma, and we choose a collection of curves, alpha 1 and alpha 2 here, and we obtain three parts, sigma 1, sigma 2, and sigma 3. And on these components here, we put finite area hyperbolic structures such that we end up with a nodal surface X here with parts X1, X2, and X3. And these curves got collapsed down to these two nodes. Okay, so I skipped over some formal aspects of the augmented moduli space, but this is roughly the idea. So how do we go from the augmented moduli space to the IRS compactification? And there's actually a rather natural way of doing this. So let's start out with a nodal surface in the augmented moduli space. And let's say it has parts xi, as in the previous image. And so in particular, we can write each xi here as the quotient h2 mod gamma I for some lattices gamma I here. And now, as in the embedding of the moduli space in the space of invariant random subgroups, we can use these to come up with a certain convex combination of IRSs to associate to our nodal surface. Namely, we define for our nodal surface X here, mu X as this sum, where we basically sum up the IRSs for each part. So here we have m parts, so the sum goes from 1 to m, and we have certain weights here, which is the Euler characteristic of the component I over the Euler characteristic of the total surface. And let me try to make sense of this definition. So first of all, we should note that for hyperbolic surfaces, the volume is a topological invariant, in fact. So for each of these xi's, we know that its hyperbolic area is minus 2 pi. It's the Euler characteristic of the component that it lives on, so of the component sigma I. And also recall that these components have negative Euler characteristics, so we put a minus here to get a positive area. Moreover, we can compute the Euler characteristic of the total surface from the Euler characteristic of its components simply by a certain inclusion-exclusion argument for the Euler characteristic. And it turns out that the Euler characteristic of the total surface is just the sum of the Euler characteristics of its parts. So together, we obtain that this definition here of mu x is actually a convex combination of the invariant random subgroups associated to each part. And one way of interpreting this weight here is just that this is the proportion of the component sigma I in the total total surface here, where we used this formula here. Okay, and now equipped with these insights, we may describe the IRS compactification of the moduli space in terms of the augmented moduli space. So how do we do this? We define a map, call it phi here. Phi goes from the augmented moduli space to the IRS compactification and sends x to mu x, which is the convex combination that I just defined on the previous slide. And we can prove that this map is a finite to one continuous surjection. So in fact, we hit everything in the IRS compactification, and this map extends the embedding of the usual moduli space. And in fact, we can be a little bit more precise about this finite to one aspect here. We can find an upper bound on the number of elements in the fiber. So we can find an upper bound, call it B sigma, on the cardinalities of its fibers. So whenever I pick a point in my IRS compactification, B sigma bounds the number of elements in the fiber of mu. And this upper bound is given by this formula here. And this looks rather complicated, but I want to just mention that here this depends only on the topology of the total surface sigma, of the underlying topological surface here. Okay, so in fact, this is a uniform bound that does not depend on mu, say, okay? And here in this formula, we denoted the Euler characteristic by chi, the genus by g, and the number of punctures by p of the topological surface sigma, respectively. Okay, so of course, I'm not just from this statement here, it's not clear that these two compactifications might not be equal, right? We could have just been able to just prove that there's an upper bound on the cardinalities, and but in fact the two compactifications coincide. However, this is not the case, as I would like to point out now by giving you an example of two nodal surfaces that map to the same point in the IRS compactification, but are actually two different nodal surfaces in the augmented moduli space. And I will try to do this with a very simple example. Namely, I will consider the three-punctured sphere, meaning I take a sphere, I take out three punctures, and I look at the associated moduli space of finite area hyperbolic surfaces on such a three-punctured sphere. And it turns out that there's only one point in this moduli space, which is a standard fact from hyperbolic geometry. And now, okay, how do I go on? I take two isometric copies of this surface x naught, and I will glue them in two different ways along their punctures to obtain two different points in the augmented moduli space. How do I do this? The first nodal surface, x1, is obtained by gluing the punctures like this. So here we have the part, here we have the unique hyperbolic surface with three punctures. And here we have an isometric copy, and we glue their punctures as depicted in the picture here. And for the second surface, we again take two copies, but this time we glue them like this, okay? And you can actually see that these are non-isomorphic nodal surfaces. However, if we just apply our map to these surfaces, we obtain that the image of x1 is by definition this weighted sum here. And let me recall to you the Euler characteristic of such a three-punctured sphere is just -1, and the Euler characteristic of a genus 2 surface, which is the underlying total surface here, is -2. So we obtain the sum of mu gamma naught, right? So mu gamma naught, right? Gamma naught is the associated lattice to x naught here, to one of these parts, right? So we obtain 2 times 1/2 this mu gamma naught, which amounts to mu gamma naught in the sum, but the same computation applies on the other side here. So in fact, these two surfaces are mapped to the same point mu gamma naught here. And that's exactly how we actually come about this upper bound in our theorem. Namely, this upper bound comes simply from, okay, given the parts with their multiplicities, in how many different ways can I pair the punctures to obtain possibly different nodal surfaces? And with this, I would like to right here, I would like to conclude my talk and thank you for your attention. And I'm looking forward to talking to you, maybe in person or at least on Discord if you have any questions about my talks. Thank you very much.